Hello, welcome to another module in this massive open online course. So, we are looking at sampling and considering impulse train based sampling, which is the most common form of sampling a continuous time analog signal to convert it into a discrete time signal. Okay. So, what we are looking at is we are looking at the principle or the theory behind sampling and trying to understand its various aspects or various properties of sampling using the Fourier transform. And what we are using is the impulse train, correct, to sample the signal. And we said the impulse train is a periodic signal delta Ts summation delta t minus kTs, k going from minus infinity to infinity. Ts, this quantity is known as the sampling duration or the sampling interval. 1 over Ts, which is Fs, is known as the sampling frequency. 2 pi over Ts, that is omega s, is the angular frequency of sampling, okay, in radians per second. Okay. And we are trying to find the coefficient Ck of the complex exponential Fourier series of the impulse train. And the CF of the impulse train, the coefficients can be found as follows. Remember Ck, this coefficient equals well over one period 1 over Ts, the fundamental period, integral over any period. So, we can choose minus Ts over 2 to Ts over 2 delta Tst or delta t. In one period it is simply delta t, delta Tst. Let me just write delta Tst e power minus j k omega s t dt. This is expression for the coefficient Ck of the complex exponential Fourier series, but in the interval minus Ts by 2 to Ts over 2, this is simply delta t. So, this is minus Ts over 2 to Ts over 2 delta t e raised to minus j k omega s t dt, which is basically, if you look at this, 1 over Ts e raised to minus, because integral with delta t is simply e raised to minus j k omega s t evaluated at t equal to 0, and therefore, this is simply equal to 1 over Ts. So, if you look at this, basically all the coefficients Ck, this is for all k. Okay. So, all the coefficients Ck are basically equal to 1 over Ts, and therefore, the complex exponential Fourier series is given as summation Ck e raised to minus summation Ck e raised to j k omega s t, all the coefficients Ck are 1 over Ts. So, this will simply be 1 over Ts summation e raised to j k omega s t, that is a complex exponential Fourier series. So, your delta Tst, which is the impulse train with sampling duration t, that is simply 1 over Ts summation k equal to minus infinity to infinity e raised to j k omega s t. This is the complex exponential Fourier series of the impulse train. This is the complex exponential Fourier series of the impulse train. Now, taking the Fourier transform, what we have is, now you recall that e raised to j k omega s t, this has a Fourier transform delta omega minus k omega s, or in fact 2 pi delta omega minus k omega s. So, if you take the Fourier transform of the impulse train, that will simply be summation 1 over Ts 2 pi delta omega minus k omega s, because the Fourier transform of each e raised to j k omega s t is simply 2 pi delta omega minus k omega s. Okay. So, therefore, if you take the Fourier transform of the impulse train, that will simply be 1 over Ts into 2 pi summation k equals minus infinity to infinity delta omega minus k omega s, which is equal to 2 pi over Ts is omega s, which is k equals minus infinity to infinity 2 pi over Ts is omega s. So, this is omega s summation k equal to minus infinity to infinity delta omega minus k omega s. Okay. All right. So, this is basically your Fourier transform of impulse train. Now, remember what are we doing? If you recall what we are doing in the sampling process, what we are doing is basically we are taking the symbol, the signal xt, and you are multiplying with the impulse train. So, this is basically multiplying the signal with the impulse train. You are multiplying the signal with the impulse train, correct. So, when you multiply two signals in the time domain, in the frequency domain, right, the corresponding Fourier transforms are convolved. So, it is given by the corresponding spectrum of the sampled signal is therefore given by the convolution of the Fourier transform of the original signal xt with that of the impulse train that we have just derived. Okay. So, next step what we want to do is we want to derive the spectrum of the sampled signal, and now you realize that is fairly simple to derive the spectrum of sampled signal. The spectrum of the sampled signal can be derived as follows. So, we have recall the property x1t multiplied by x2t, the corresponding Fourier transform is 1 over 2 pi x1 omega convolved with x2 omega. Okay. Now, therefore, now recall that our sampled signal xst is the product of the original signal xt with the impulse train, that is delta st. Okay. So, this is your sampled signal. Which implies its Fourier transform is going to be x of omega. In fact, there has to be a constant factor of 1 over 2 pi, 1 over 2 pi x of omega convolved with the spectrum delta Ts, let us call this delta Ts of omega or whatever. So, convolved with the spectrum of the impulse train, that is delta Ts omega, which is basically equal to 1 over 2 pi x of omega convolved with omega s summation k equal to minus infinity to infinity x of omega minus k omega s, and I am sorry, delta omega summation k equal to minus infinity to infinity delta omega minus k omega s, now which is basically omega s over 2 pi. Now omega s over 2 pi, remember that is fs, which is 1 over Ts. So this is 1 over Ts, taking the, since the convolution operator is associative, taking the convolution operator inside, xn convolved, x omega convolved with delta omega minus k omega s, which is equal to, now x of omega convolved with delta omega minus k omega s is simply, when you convolved with shifted impulse by k omega, it is simply shifting the function, that is x of omega shifted to omega s, that is we get x of omega minus k omega s. So this will be basically 1 over Ts summation k equal to minus infinity to infinity x of omega minus k omega s. This is the spectrum of the, this is the spectrum of the sampled signal, spectrum of the sampled signal, signal sampled by the impulse train. Okay. This is the spectrum of the sampled signal. Okay, and you can see this is basically shifting and adding. So what you are doing is x of omega, you are shifting it by each integral multiple of omega s, that is you are shifting it by omegas, that is x of omega minus omega s, you are shifting it by 2 omega s, that is x of omega minus 2 omega s. Similarly, you are shifting it on the negative side, that is x of omega plus 2 omega s, x of omega plus omega s, so on, and you are basically adding all these shifted copies of the original spectrum xw. So basically it is a summation or sum shifted and added spectra of the original message signal xw. It is the sum of the shifted, and so these are replicas, right, these are replicas of the original spectrum x omega shifted by every integral multiple of the sampling frequency omega s, and then all these shifted replicas are basically added. Okay. Now consider, now let me describe this pictorially, describe this process pictorially. Consider x of omega given as shown below, and we have, let us say we have a maximum spectrum that looks something like this. Okay, this is omega m. So x of omega equal to 0 for omega magnitude of omega greater than or equal to omega m, that is either omega greater than or equal to omega m or minus omega less than or equal to minus omega m. Okay, so omega is the spectrum is 0. So what we are saying is this omega m, this is equal to the maximum frequency. So this is the maximum frequency of the signal omega, that is x of omega is 0 when omega is greater than omega m as well as when omega is less than minus omega m. So x of omega is restricted to this band minus omega m to omega m. So you can say omega m is the bandwidth of the signal. Okay, basically omega m is the bandwidth of the signal. Okay, the signal is 0 outside of this bandwidth. Now if you consider this signal, which is x of the spectrum of the sampled signal, which is basically scaled by 1 over 2s. Let us say the original signal is scaled unity. So, basically this is 1 over Ts summation k equals minus infinity to infinity x of omega minus k omega s, that as we said consists of shifted replicas of the original signal. So, you have one, you have another that is shifted, you have another that is shifted, and you have another that is shifted by 2 time or shifted to minus 2 omega s. So, this is shifted to omega s, this is 0, this is minus omega s minus 2 omega s. So, this is your original copy, each is scaled by 1 over Ts. This is your original copy, that is x of omega, this is x of omega minus omega s, and then you will have several copies over here. Similarly, this is your x of omega plus omega s, this is x of omega plus 2 omega s, and so on. And now, if you look at it, something interesting happens. If you look at this point, this is omega m, and this point of the shifted one is omega s minus omega m. Now, you look at this gap, if omega s minus omega m is greater than or equal to omega m, then you will have this gap, correct, which implies that these two spectral copies corresponding to x of omega and x of omega minus omega s, these two do not overlap. As a result, they will not interfere with each other, and that will happen when there is a gap, and for there to be this gap or this guard band between the original spectrum and its various shifted copies, this condition has to be satisfied, that is omega s minus omega m, the maximum frequency, has to be greater than or equal to omega m, which implies basically now the condition that omega s greater than or equal to omega m. And this quantity omega s is the sampling frequency, omega m is the maximum frequency. So, if this is satisfied, this implies there is no interference from the spectral overlap, no interference or distortion. From spectral overlap. However, if this condition is not satisfied, that is if omega s minus omega m is or omega m is greater than omega s minus omega m, if this condition is not satisfied, then you can see what happens. If this condition is not satisfied, then you will have your original copy, that is your 1 over Ts, and then you will have another copy. So, this is your omega m and this is your omega s minus omega m, which is less than omega m. So, this quantity is where there is overlap, and that causes distortion, which is termed as aliasing. So, what happens in this scenario is that omega s minus omega m is less than omega m, implies omega s is less than twice omega m, implies overlap, which is basically equal to aliasing. This is a distortion. So, this basically when these spectral copies, when they overlap, right, they superimpose over each other, that leads to distortion of the original spectrum. Then you cannot recover the original message spectrum by any kind of filtering operation. Hence, this is termed as aliasing. This distortion which is resulting from undersampling. Remember, you will have no distortion if omega s is greater than or equal to twice omega m. When omega s is less than twice omega m, you will have this distortion which is termed as aliasing. And this criteria for no aliasing, this is termed as the Nyquist sampling theorem or the Nyquist criterion for no aliasing. Okay. So, for no aliasing, so we need omega s greater than or equal to 2 omega. This is the criterion that we need for no distortion. Okay. And this is termed as the Nyquist sampling theorem. Nyquist sampling theorem or the Nyquist criterion. This is termed as the Nyquist sampling theorem or this is termed as the Nyquist criterion. Okay. So, for no overlap, so for no distortion, no spectral distortion, we need to have this sampling frequency greater than or equal to twice into the maximum frequency of the. So, the sampling frequency has to be greater than or equal to the sampling frequency. So, to avoid aliasing, and this is also termed as the Nyquist rate, this 2 omega m, this is also termed as the Nyquist rate, or basically the minimum rate at which the signal has to be sampled so that there is no distortion. This is a very important property, one of the key properties, alright, which one of the key properties which has to be kept in mind, which has to be borne in mind when converting a signal from the analog to the discrete time or the continuous time to the discrete time domain via sampling, alright. So, if the sampling frequency, alright, to avoid aliasing, the sampling frequency omega s has to satisfy this key criterion, alright. So, this minimum threshold that omega s must be greater than twice the maximum frequency of the signal. If it is less than twice the maximum frequency, then there is going to be distortion. This is termed as aliasing, and therefore, this quantity 2 omega m is termed as the Nyquist rate of sampling a signal, and this is the minimum rate of sampling a signal, band limited signal, to avoid aliasing distortion. Alright. So, I will stop here and continue in the subsequent modules. Thank you very much.